The game we were just playing relied on one very crucial number that for the longest time was absent from mathematics, and that is 0. The oldest record of a 0 symbol dates back 5,000 years to ancient Mesopotamia. The ancient Babylonians originally had no symbol and would instead leave a space where we'd now use a 0. This was likely really confusing, and so a 0 symbol was eventually introduced to make reading numbers easier. The Mayans used an upside down tortoiseshell to denote 0. The Babylonian and Mayans didn't view 0 as a number in its own right, treating 0 as a mere placeholder to show that there was no numbers in that column. In India, 0 was initially seen as a placeholder as well, but then Indian mathematicians made 0 a number in its own right by showing that some equations produced a 0 as an answer. The Bakshaki manuscript from 350 AD is thought to be the oldest document to feature our modern concept of 0, and the 0 symbol has been in use in India since at least 650 AD. Indian mathematician Brahmagupta called 0 shunya, meaning void or empty, and noted how subtracting a number from itself gave 0, as did multiplying a number by 0. 0 spread throughout the world via merchants as they travelled along trade routes such as the Silk Road. In the 10th century, the Arabs adopted the Indian number system, with the Arabic word sifa, also meaning empty, being used to describe this number. Fibonacci's book Libra Bacchi was key in introducing 0 and the Indian number system to the West. However, it would take until the end of the 1400s for Arabic numerals to completely usurp Roman numerals as the dominant number system. Part of the reason it took so long for 0 and Arabic numerals to be accepted in the West was because they were introduced right in the middle of the Crusades against Islam. At this time, the church was suspicious of anything of Arabic origin, labelling such numbers as the devil's work. There were also concerns about how a 0 could be easily changed into a 6 or a 9, or how a 1 could become a 7. This would make documents much easier to doctor. Roman numerals were far too rigid and precise for such things. This fear resulted in the city of Florence banning the use of 0 in 1299. 0 is a very strange number. If you add something to 0, nothing happens. Same as if you subtract 0. But if you multiply by 0, the whole number is obliterated into nothingness, becoming 0 itself. The real weirdness, however, comes when you try to divide by 0, or raise 0 to the power of itself, both of which are impossible. 0 paved the way for another kind of number that was initially met with skepticism: negative numbers. Negative numbers have given people many centuries of headache and confusion, which could be why to this day, underground floors are numbered B1, B2, B3, instead of using negative numbers. Neither ancient Greek or Babylonian mathematicians had a concept of negative numbers. This is fairly understandable, as on the surface, they don't make much sense. You can have 1 cow, or 2 cows, or 5 cows, but you can't have negative 4 cows. That's nonsensical. How can you have 4 cows less than no cows? The very idea of less than nothing quite naturally seems absurd. However, if we peer closer, we can find real-life uses for negative numbers. The best examples involve debts. If I lend you £10, you have a debt of minus £10. They'll only become 0 when you give that £10 back to me. A way I like to think about negative numbers is in terms of years. My current age is 22 years old, as I was born in 2001. So I am plus 22 years old. Thinking this way, you could just as easily go back to before I was born and assign my age as a negative number. For instance, in 1986, I was negative 15 years old, negative 30 years old in 1971, and negative 55 in 1946. This may seem silly, but we already do it with the birth of Jesus. AD describes the number of years after Christ's birth, and BC represents the amount of years before his birth. Instead of using AD and BC, we could just as easily use positive and negative years, and everything would work just as nicely. The ancient Chinese were potentially the first to dip their toes into the concept of negative numbers, allowing the use of them to a certain extent. They had a calculation system involving rods, Normal rods represented positive numbers and were called true, whilst rods painted black denoted negative numbers and were labelled as false. If a calculation gave an answer made of normal rods, it was considered a true number and was accepted. And if the answer was made of black rods, it was considered a false number and was rejected. In the 7th century, Brahmagupta created a series of equations describing how negative and positive numbers behaved with zero. He used debts to describe negative numbers and fortunes to describe positive numbers. By that logic, £1 is a fortune and everybody is rich. The statements were expressed with these words here, and if we write them in algebra, they look like this. An early proponent of the Indian number system featuring zero and negative numbers was the Arab mathematician Muhammad ibn Musa al-Khwarizmi, known as the inventor of algebra. Through the use of algebra, European mathematicians finally began to accept zero and negative numbers. There was still much resistance to them right up until the 17th century, when they were finally fully accepted. In the 15th and 16th century, negative numbers were mockingly called absurd numbers. Mathematicians were so against using them that the quadratic equation wasn't even a thing, with 6 different quadratic equations being used. These were all arranged in such a way that the coefficients were always positive. In 1685, John Wallis came up with a visualization that allowed negative numbers to finally be fully accepted. He pictured a number line with positive and negative numbers going out from zero in both directions, and imagined positive numbers as steps to the right or steps forward, and negative numbers as steps to the left or steps backward. So +3 is 3 steps forward and -2 is 2 steps back. Negative numbers themselves lead to an interesting problem. If we multiply 2 positive numbers, we get a positive number, and multiplying 2 negative numbers also gives a positive number. This means that a positive number squared is positive, and a negative number squared is also positive, and therefore there's no kind of number that can be squared to give a negative number. This must mean that the square root of -1 is impossible, and therefore has no solution, right? Well, not quite. For a long time, mathematicians thought exactly that. It wasn't until the 16th century that it all began to change. Mathematicians had begun to encounter equations that, when you tried to solve them, contained steps involving roots of negative numbers. The thing is that these equations are perfectly solvable and have actual solutions, such as this equation here. Enter imaginary numbers. Italian mathematician Girolamo Cardano was the first to propose that whilst the square root of -1 had no actual value, it could have a kind of fictitious value, referring to such numbers as fictitious numbers. Cardano didn't get very far with them though, and said that thinking about it caused him mental torture, as it would anyone else who hadn't encountered them before, declaring equations that used them to be as refined as they are useless. 10 years later, Raphael Bombelli resurrected the idea. He made the square root of a negative its own kind of number, and treated it just the same as he would any other number. By doing this, he discovered that not only was the maths 100% consistent, it actually allowed previously unsolvable equations to be solved. René Descartes coined the term imaginary as a way of mocking the idea of them, and the I symbol was then later introduced by Leonhard Euler to represent such numbers. In 1831, Gauss came up with the term complex number to describe numbers created by adding together a real number and an imaginary number. Imaginary and complex numbers were both accepted more when the complex plane was introduced, which gave a visual representation of these numbers. Let's take a look at the complex plane and complex numbers. The real number line, as we will now call it, extends out to infinity in opposite directions, to positive and negative infinity. If we want to put imaginary numbers on this line, we can create a new imaginary axis perpendicular to the real number line and intersecting at 0. We can then put I 1 unit away from 0, 2i, 2 units away, 3i, 3 units away, and so on. We can also go the other way, creating negative imaginary numbers. Now that we have our imaginary axis, we can start to create complex numbers by going 2 units across on the real axis and 3 units up on the imaginary axis. We can create 2 plus 3i. If we go 5 units across on the real axis and 4 units down, we get 5 minus 4i. Complex numbers are simply a coordinate system for describing a whole new set of numbers that exist on a two-dimensional plane. What happens when we add or multiply complex numbers? Let's see. Multiplying by I can be thought of as doing a 90-degree rotation through the complex plane. 1 times I is I times I is -1, -1 times I is -I, and -I times I is 1. We can then extend this to say that multiplying by -1 is taking a 180-degree rotation through the complex plane, which is evidenced in our positive and negative number line. And multiplying by just 1 is taking a 360-degree rotation through the complex plane. Although we don't normally think of multiplying by 1 in this way, it is a completely accurate way of thinking about it. We can also do this with other angles as well. Let's create a unit circle around the 0 point going through the complex plane. To find the complex number that can represent a certain angle of rotation, we can use our good friend trigonometry. Such an angle can be calculated with the formula cosine theta plus I times sine theta. Multiplying any number by this corresponds to a rotation of theta degrees. To do a rotation of 45 degrees, you can use 1 over root 2 plus 1 over root 2 times I. Multiplying this by itself gives you I, and so the square root of I is an imaginary number itself, and not some kind of weird new number. To do a rotation of 60 degrees, multiply by a half plus root 3 over 2 times I. To do a rotation of 30 degrees, multiply by root 3 over 2 plus a half I. Because they can be used to model rotations, imaginary numbers have various real-world uses. Schrödinger's wave equation uses imaginary numbers and is used to calculate the probability of a subatomic particle being in a particular location. They've also been used in calculations of alternating current, relativity theory, signal processing, fluid dynamics, and quantum mechanics. If complex numbers can model two-dimensional rotations, you may be wondering, what kind of numbers model 3D rotations? It may seem like we'd need 3 sets of numbers because we used 2 sets of numbers for 2D rotations. However, this isn't true at all, and you actually need 4 sets of numbers or 4-dimensional numbers known as quaternions to describe 3D rotations. Quaternions have been used to represent 3-dimensional movement in video game programming, computer graphics, molecular modeling, signal processing, robotics, bioinformatics, and the geometry of space-time. The flight software of the Space Shuttle also uses quaternions for its navigation, guidance computation, and flight controls. Quaternions were developed in 1843 by Irish mathematician William Rowan Hamilton. They can be represented using 4 units in the way shown here. Q equals A plus BI plus CJ plus DK. Each of the imaginary units, I, J, and K, are equal to the square root of -1, still completely different numbers. This is similar to how -2 and 2 are both the square root of 4. The equations for quaternions are in the form shown here. Hamilton carved these formulas into the stones of Brum Bridge in Dublin after insulation struck whilst he was walking along the canal with his wife. Hamilton had been trying to make a working system of numbers with just 3 units and had failed, but found that everything fit together with 4 units. If you want to find a number system for describing 4-dimensional rotations, you can't do it with 5, 6, or 7 units. However, 8-dimensional units work perfectly, being known as octonions. Octonions are still waiting to be given a purpose, with one possible application being M-theory, a version of string theory that postulates the existence of 8 extra dimensions.